Okay, good morning all. So today in this session we will first go through the problem of DAA instruction. Okay, so it was asked in my last class. So I am just clearing the DAA instruction, and then we'll start the our next topic, that is microcontroller. Okay, and you can see that I have already submitted yesterday one assignment for you. So you have to submit that assignment by Saturday 16th, and I cannot extend the deadline because we have to take this kind of assignment weekly. Okay, so it is mandatory to to give you assignment weekly and take it weekly, right? So what I have done, that in that assignment you can see that there are 10 questions. Among the 10 questions, first 6 questions are very straightforward, and next 4 questions are little tricky. Okay, so it is not too much tough, so that hardly it will take 30 to 40 minutes. Okay, so I suggest that you just submit the assignment within the stipulated time that I have mentioned there. Okay, and you can see also 20 marks is assigned to that assignment. So 2 marks for each question, and to be your answer should be very precise. So don't write extra things. Okay, only 2 marks are assigned for each question, so just write the answer only. Okay, so that is the regarding your assignment. And now the instruction DAA, as it was asked in my last class that sir, could you explain the instruction DAA? So I am just giving a brief of that instruction. Okay, so actually the full form of DAA instruction is the Decimal Adjust Accumulator. Okay, so you can write it down. The full form of DAA instruction is Decimal Adjust Accumulator. Okay, so what is this? What is the meaning of Decimal Adjust Accumulator? The meaning is very simple. So we are dealing with the hexadecimal number, which is nothing but the combination of binary numbers. Okay, so basically we are dealing with hexadecimal number system, and using DAA instruction we can convert that hexadecimal number to decimal number system. So DAA instruction is instruction by which we can convert hexadecimal number to decimal number system. Okay, now the question is, in the hexadecimal number system there is number after 9, right? That is A, B, C, D, E, F, right? So but in decimal number system these digits are doesn't exist, these digits are not exist. Okay, so what happened while converting this kind of digit from hexadecimal to a decimal number? So there is a some rules we need to follow for that purpose. So what is that rules? So that rules I will discuss. So basically DAA instruction is used to convert the hexadecimal to decimal number. Now suppose you are adding two number. Okay, suppose you are adding two decimal number, okay, in 8085. So what does it mean? It means that you are adding two numbers which are, you know, that in decimal form, but the 8085 does not know that the numbers are in decimal format. So while you are taking that number as a decimal, you are understanding that the number is in decimal, but 8085 understands that the number is in hexadecimal. So suppose what happened, you can see from this figure, 2050 there is a location and 2051 there is a location. So in these two locations, two data are stored. So initially two data are stored, and user has given this data. Okay, now user has given this two data in the decimal format, right? So that means user can give any combination of digit from 0 to 9 for data 1, also any combination of digit for 0 to 9 for data 2. Okay, so user has given this thing. Now user wants that using 8085 key, user wants to add these two numbers, okay, and want that the result should be in the decimal format. So this is actually user wish. So you can see that in the problem statement it is written decimal addition of two 8-bit number. Okay. Excuse me. And sum 16-bit in decimal. So you can understand that what is the aim of this program. The aim of this program is adding two decimal number and result also a 16-bit formation in the decimal. Okay, so here you can see two 8-bit numbers. When in the decimal format we are adding these two numbers, we are getting a result in 16-bit, not 8-bit. Okay, and that 16-bit result is in the decimal format. So some rules we need to follow, because this data 1 and data 2, though it is in the decimal format, but we are using 8085 key. So when 8085 key adding this to data, okay, so you can see that which instruction I have used. I have used LXI. Okay, so pointing first in address, then I am moving carry register 00. Okay, then I am moving the first element to accumulator. I am increasing the HL register pair location. Okay, then I am doing addition. So you can see that up to this add aim, whatever the addition is happening, means at the line add aim, the addition is happening here. So this addition at the line, this add aim in the hexadecimal mode, right? But after this step I have used a instruction DAA. So after addition I have to use this instruction DAA. Okay, so that the result, or that means you can see the equation, accumulator plus content of memory location will be added. Okay, then the result stored at the accumulator. So DAA directly act with acts upon this accumulator content and convert that content into decimal. Okay, then I have to take care that whether there is carry or not. If I get a carry, then I have to increase the value of carry flag, then I have to store the result, then I have to store the carry. So if I take out this instruction DAA, okay, then you can see the program flow is just like the addition of two numbers and storing the result and carry into two different locations. Okay, so here, okay. So this is the thing. So you can take out the instruction DAA and you see that what is happening here, just addition of two numbers and storing the result and carry into two different locations. So this is the thing we have already performed in our lab experiment, but here only one instruction I have added extra, that is DAA after addition. So that will actually that will make the difference, that will make the difference. Which difference? That will convert the result into decimal, and while converting result into decimal, some rules are followed. So which rules are followed? So I have written these rules here. Okay, so you can see DAA, decimal adjust accumulator. Okay, before going to this thing, I just want to say that this document that I am showing, it is actually your, I have already shared it with you, 8085 stack related problem. So in that PDF you can see this DA instruction. Okay, so just one second. Okay, so the rules. So which rules are used here? So you can see the DA is the decimal adjust accumulator. So it will add 06 it will add 06. This is the thumb rule. It will add 06. Okay, while LSB, it will add 06 to the LSB. What is LSB? LSB is nothing but the result is your 16 bit, right? Let me go to the little upper side. So add M. So you are doing addition. So you are getting the result here in accumulator. Okay, and accumulator content is 8 bit, right? Okay, okay. So that among that 8 bit, from the left side, first 8 bit, first 4 bits are LSB part, and next 4 bits are MSB part. Okay, I have also shown here, so no problem. So you can see that what is the I have written accumulator content LSB then MSB. So upper 4 bits MSB, lower 4 bits LSB. Okay, so that you can match this thing. So what happened? Thumb rules. First thumb rule is you have to add 06 to this lower LSB part. When the content of the LSB in the range of A to F. Okay, you understand? That digits creates problem because these are not exist. They are not exist in the decimal number system. So A to F, when there is in the LSB, you can see that the digits are between A to F. You have to add 6. Okay, so this is the case first. Also, you have to add 06 if the auxiliary carry is 1. So when auxiliary carry is 1, you have to add 06 here. So that means what does it mean auxiliary carry? It means when I am doing this addition operation, okay, when I am doing the addition operation, there may be a case when auxiliary carry will set. Okay, so in that case you have to add 06 to the 4 bits. Though in that situation you see the LSB is not in the range of A to F, so it is written as OR. So if you can see in the LSB part that this is not in the range of A to F, but you see the auxiliary carry is 1 in the previous step, that means in addition step. So in that case also you have to add this LSB 4 bits 06, and similar to that upper one also. So you have already added accumulator with memory location value. So you may get carry in that addition. So if you get that carry, or if the content of the MSB in the range of A to F, then you have to add 4 bits. Okay, so this is the thumb rule. So you can it is very feasible when I explain the example. So first example I have taken all the cases. So first example, you can see the two decimal number the user has entered 96 and 69. So very simple, two numbers 96 and 69. So this user has given this number, so I have written decimal format DD. But uh, in when the exaggerate for adding these two number, okay, so it is handling this number in hexadecimal. So I have just break this number into binary, then add it number. So so it is AC. AC means what? Your accumulator. So after addition, this result is in your accumulator. And what is the content of accumulator? So this is actually nothing but FF. Okay, so you can see that this is FF, right? So and what is the content of this LSB? So this is actually F, which is in the range of A to F. So you have to add 06 here. Okay, and what is the content of upper side? So this is also your F, so you have to add 06 here. So this is the very simple first and very simple most example where you can see that both LSB or MSB are in the range of A to F. Okay, so this is very straightforward example where I am adding two numbers in the decimal, but after adding these numbers in the accumulator content in the hexadecimal is FF. So both the digits are in the range of A to F. So you have to add 06 in both digits. Okay. So coming to the next one. So you are when we are I am adding 06. So you just see that what I am getting. what I am getting, so while I am adding this 06 with 15, so this is 15, so I am getting 5, 1, 110, 110, then 1, 110. Okay, 0, 1, 0, 1, then 1 is coming here, 110, then 1, 1, 1, and there is a carry. Okay, so that means the content of accumulator is now 65. You understand? 6 in the upper side, 5 in the lower side. So this is actually your decimal result. Now what I have written here, I have written this is hexadecimal, but I have written here D. That means this is your decimal format, right? 65, and as well as you are getting a carry. So carry is 01, right? So what we will do after getting this carry? So you just go to the program. If I go to the program, you can understand. So after this DA instruction, jump on no carry. If I'm not getting any carry, then I'm directly storing the result. Now if I, while I am getting carry, I am increasing the C register value. So it is 01, then I am storing the content of accumulator this, then I am storing the, then shifting the content of C to accumulator, then I am writing it to next location. So what we will get, you get at the location 2501, okay, and 2500, 01, and 65. Okay, so this is your final result. Now you just compare this result with normal addition, normal decimal addition. So if I decimally added these two things, what you will get? You get 165, right? So here I am also getting 165. So you understand that how I am getting 165. That means in this program, what I have just entered, I have entered only one instruction DAA after addition, that will do all the all this hidden work. Okay, so it will add a while after addition. So addition will done in a normal way when I am doing add m. So these two values are added and result stored in the accumulator. Then I am using DAA. So DAA when I am using, so microprocessor will check these two digit LSB and MSB, and it checks that both these digits are in the range of A to F. So it is adding these two numbers 0606 with this two digits, and after addition, just a simple addition, you are getting a carry, you are getting a result. So you are storing the carry at a different location and storing the result in a different location. So combining these two location, I am getting the final result, that is 165. Now you compare with the given numbers 695, 15, 69, 16. So 165. So this is result is matching. So this is your decimally added value. Now I am going to next example where you can see the next condition. The condition is, here you are adding two decimal numbers similar to the previous one, 84, 92. So 84, 92, 92. So 4 plus 2, you are getting 6, and 9 plus 8. So you are getting a carry here. Okay. So you are getting 6, that is no problem. But while you are adding 9 and 8, so you are getting 1 here and 1 carry here. So the condition is, then you have to use DAA. So DAA, while DAA when you use, it will check the LSB part. So I have written here LSB is not in the range of A to F, right? So it is okay. But MSB also is not in the range of A to F. So so this condition is satisfied. But you see, what is the next condition for the checking MSB? You have to check also the carry flag status. So I'm checking the carry flag status. So I'm getting MSB also in the not in the range of A2F, but I'm getting a carry flag. Okay, then I have to add 06 here. So I have to add 06 here. So I'm adding the 06 with this given result, accumulator result. So DAA, so DAA will add 06 here. Okay. So after adding 06, what I am getting? So this is 6, and here it is coming as 7. So 6 and 76. Okay, and what I am getting? So 1 is 1 1 1 and carry. So this carry is not coming from this carry is previously already generated carry. Okay, so I am actually getting, so you just see the carry flag is already set. Okay, so while you are adding this thing, so I'm going back to the program. So while we are adding this instruction add m, so it is adding this to value 8492, and then you are using DAA, so it is adding the result 06, adding 06 to the MSB, right? So it is adding 60 to the MSB. So 60, that means you are adding, hitting the MSB part, you are adding 60 to the MSB, and already there is a carry, so J and C will false, so it will increase the carry content. Okay, and then what it will do, it will store the result, it will store the carry. Okay, so that means here after addition, you are getting 76, and here you are getting 01. Okay, so that means finally you are adding just two values, so 426 897, so 176, so you also getting 176 as your result. Okay, so that means in this example what we see that though the MSB and LSB both the digits are not in the range of A to F, microprocessor has to check whether the status of the auxiliary carry and carry flag. So I have not written here auxiliary carry because you see while these two 00 are adding, there is no chance of setting the auxiliary carry. So auxiliary carry depends upon when from this digit, this is D3 digit, to this is D4 digit. So when there is a internal carry is passing from this to this, then auxiliary carry is set. So there is no chance of setting auxiliary carry here. So microprocessor will see that a carry flag is set. So microprocessor will understand that I have to add 60 with this result of accumulator. Then I have to take care of the carry also and the content of accumulator also. So this will give you a complete result. Okay, so I have already discussed two examples. So first example is the example where microprocessor is getting for MSB and LSB for both of digits, the range result is in the range of A to F. Okay, that is very straightforward and simple example where microprocessor just see the result, both are in the range of A to F. That means microprocessor have to add the 66 66, both the digits 6 and 6, 66, right? Okay, and the next example what I see, microprocessor after addition, the content of accumulator is such that the both of the MSB and LSB are not in the range of A to F. So microprocessor will then go to check the status of auxiliary carry and carry. So it will see auxiliary carry is 0, but carry is 1. So microprocessor will understand that I have to add 60 with the content of accumulator. So it is adding 60, taking care of carry also, that is already previously generated, and the new content of accumulator, that is 76. Okay, and now the third example. In the third example what we see, we are adding to number that is 98 with 99. So 198 and 99, so what you will get, so you get 1 here and 0 0, then after adding 110 here, so 1 is passing to next digit, that means it will set the auxiliary carry. So I have mentioned here, so auxiliary carry will generate it. Okay, then you are passing 1 here, so 110 and adding to 1, that you are getting 1, then again 1 here, then 0 here, then 110, then 1 here. So in this case what microprocessor will understand, okay, so you are adding these two digits, sorry, we are adding these two digits, after addition the content of accumulator is 31. So content of accumulator is 31. So microprocessor will check the content of accumulator, so it is actually 31. So microprocessor then next what microprocessor will do, it will check the status of auxiliary carry and carry. So microprocessor will see that both are generated. Okay, so it is written the accumulator content is 31, both auxiliary and carry flags generated, so 6 must be added the both of the MSB LSB. So microcontroller will add the 6 here, microcontroller adds 6 here. So you just see what is happening here. 1 1 1 here 0, okay, and 1 1 0 1 1 0 1. So you are getting 97, 97, and already you have previously get it, you have received that carry 1, so 0 1, okay. So that means you can see that if you add these two numbers, what you will get, you will get 197. So that thing is here coming. Same thing is coming here, 197. So Microsoft will store these results to different location. So what is the result after addition? So I have shown you clearly, you can see. So how to interpret the result? So this is the location of the data, 98 99. After addition, this is the location of the data for the result, 0197. So 9190197 is the result. So 0197 is basically a decimal result of the this two addition of these two decimal digit. Okay. So this is all about DAA instruction. So DAA very important instruction. It will add, it will convert the content of accumulator to the decimal. But what is the content of accumulator? Content of accumulator after addition. So without addition, if you use just, so if you use just a DAA, then it will not give you a proper result. Okay. So means what I mean means you are shifting some data to accumulator, then just check means move m comma a. So after this instruction, if I write the DAA, then it will not give you a proper result because there is no addition operation happened. So then it will just give you some arbitrary or wrong result. Okay. So DAA instruction is not used to convert accumulator content into decimal. It will convert the accumulator content to decimal after the addition. After the addition of two decimal numbers. Okay. So after the addition of two decimal numbers, it will convert the content of accumulator into a decimal. Because you see, if I use DAA after MOV A comma M, then how I can follow the this to thumb rule, because it may happen that the content of accumulator is not in the range of these two conditions are failed, but there is no provision for checking auxiliary carry and carry flag because there is no arithmetic operations has happened, right? So if there is some previously arithmetic operations has happened, then depending on that arithmetic operation, if I change the content of accumulator, then there is a lot of discrepancies, though this is not a good way to convert the content of accumulator into decimal. Okay, so only when you are adding to decimal number, right, and then you are converting your result into decimal, then you can use DAA instruction. I think it is clear. Okay, I get a question. If the carry flag is not present in the okay, if the carry flag is not present in the problem, if the carry flag is not present in the problem, okay, carry flag is not carry flag. Basically, initially there is no carry flag. Okay, so you can see that here while I am executing this instruction, so there is no condition, no case for carry flag. Now when I am adding these two value, then the carry flag will come. So maybe carry is generated at this step. So in example 2, so I'm going to example 2. Okay, so here if your question is if the carry flag is not present in the problem, so suppose you are suppose you are adding some value, suppose you are adding say 24 with 62. Okay, so just reverse the things. Okay, so suppose you are adding 24 with 42 here. So what will happen? Is there any carry? No carry. So there is no, then there, if there is no carry and the MSB not in the range of A to F, then microprocessor will do nothing. Okay, you understand that if there is no carry as well as the content of the accumulator is not in the range of A to F, then the result is itself in the decimal form. The example of that is that suppose you are adding 24 with 42. So what you will get? You will get 66. 24 with 42, you will get 66. So 66 means what? The content of lower LSB is not in the range of A to F, upper is not in the range of A to F, not on no auxiliary carry flag, no carry flag is generated. Okay, so it is high. Yes, the number itself in the decimal form. So the conditions, the thumb rules arises only when after addition you are getting something in the range of A to F, or internally the carry flag or auxiliary carry flag is setting up. Okay, and, or the thing, or the thing is like that. While suppose, just for this example, you can see 8 plus 9, so it is 17. So I cannot write or convert 17 in a four digit of binary combination. I have to take 5 digit. Okay, so basically it is not in the range of hexadecimal also. So 4 digit hexadecimal, it is not possible to represent the added value of 9 plus 8. Is it possible? Addition of 9 plus 8, okay, to convert this result into a 4 digit hexadecimal, it is not possible, because 4 digit we can maximum value we can represent is 15. So I have to represent 17 here, so it is not possible. I have to take extra one bit at the left side, so that is here carry bit. So for that reason, we understand that this range, the result after this 9 plus 8, is beyond A to F. Not only A to F, it is beyond A to F. So that means microprocessor have to have add 06 here. Okay. So this is how we can also see. We can also understand that when I am getting carry, that means it is not only in the range of A to F, it is beyond that. So microprocessor have to have add 06. Similarly to this also, this side also, when I am getting something in the auxiliary carry flag, so that means this four digits addition added value is beyond A to A. So microprocessor have to have add 6 here, right? So you can see here 9 plus 8, so you are getting 70. So that is not possible to represent here in with this LSB 4 digit. So that's why auxiliary carry flag is 1. So in this case also, I have to add 6 with the LSB part. So this is all about this part. Okay, next, 1 second. So uh, so I am sharing the another document. Okay, so is it visible? I think, is it visible? Okay, another question is there in the example 3, how auxiliary carry flag is set. Okay, in the example 3 you can see that auxiliary carry flag will set when, how the binary digits are represented. This is D0 bit, D0, D1, D2, D3, D4, D5, D6, D7. And what is the definition of auxiliary carry? When from D3 to D4 a carry is transferring or passing, right? So when I am adding this D3 digit 1 1, so I am getting 0 here, and I am passing 1 from this D3 to D4. So for this condition, auxiliary carry will generate. So auxiliary carry will generate when there is a carry, means in between carry is passing from D3 to D4. Okay, so this is the answer of the question, how auxiliary carry flag is set in this example 3. Okay, now I am sharing a second document, microcontroller PDF document. Can you see this document? Okay, so microcontroller document is visible. So just one second. So uh, so this is the next topic we understand. We try to understand, that is the microcontroller document. So in the microcontroller, what is the basically a introduction of the microcontroller? Here in this subject of your semester, this subject name is microprocessor and microcontroller. That means not only we have to understand microprocessor in its operation, we have to understand little bit at least what is the basic functionalities, how microprocessor microcontroller are different in the mode of operations, in the mode of architecture. So this kind of little things we have to understand. Okay, so according to the syllabus, according to the purpose, so we are proceeding to that direction. So you can see that microprocessor and microcontroller, as there are two different topics are merged with this in this subject. So there is a very specific purpose for this. So if I figure it, when I am figuring this thing out, what is the main actually the purpose? The purpose is in the advanced in the current situation, you see that there are very advanced kind of microprocessor and microcontroller are available. Okay, so but the core thing, the core operations of these two different structures, a core diagram, block diagram, and core instruction set, how they are operate, the core things are still same. So so what is happening basically when we are manufacturing a microcontroller? Okay, so in our back of our mind, we always see, or we always think about that, where we have to do some specific task. We have to perform some specific task. Okay, and when I'm manufacturing a microprocessor, then I have to think that I have to build a device that can that can be used for wide application purpose. Okay, so this is actually the difference. So at first we understand the wide application device, that is your microprocessor. So and I have just shown you very small part of this because according to the syllabus I have to go forward. But there are so many peripheral devices we can connect. Okay, we can connect printer, we can connect keyboard, we can connect LED, we can connect switches, we can connect different analog circuits, we can convert analog to digital converter. Okay, analog to digital converters while connecting some analog system with this microprocessor, and while connecting some digital system, then we can directly connect through peripheral devices. So there are lots of peripheral devices we can easily connect with microprocessor. Okay, so so that means there is a huge kind of application for the microprocessor. So in that, for that purpose, in the block diagram of the microprocessor you will see very small number of units are there. So that means manufacturer wants that if you want to use a microprocessor for processing purpose, so you have to provide data from outside. Okay, you have to provide your data or whatever the things you want to do, you have to provide it from outside. You have to connect it to the microprocessor, then operate it. So basically a microprocessor is a heart, or is a key part of a complete system. Okay, while a microcontroller is a itself a system on chip. Basically what? A system, a complete system on a single chip. That means it is performing a very specific task and it doesn't require any extra peripheral device to connect with it to complete that task. So all the required hardware are present in the chip, also in the chip itself. Okay, so you can see in the block diagram of the microcontroller there are multiple number of units are there. So that is the reason the microcontroller are used as a device which is very much known as system on chip or application specific integrated circuit. This kind of keywords are associated with the microcontroller. And while in the microprocessor, it is used as a wide application purpose. Okay. So basically, in this subject, we try to introduce you with these two kind of architectures. Okay, so that in the future, if you want to further study or if you want to work with this, so you can easily grab the concept that which one you want to take it out. Means which one you have to select, microprocessor or microcontroller. If it is microcontroller, then how many integrated part, how many external, that means how many units you want to integrate in the single chip. Okay, so this kind of thinking to process to we are try to implant into you. So that for that purpose, here in this subject you see there is a microprocessor as well as microcontroller. These two topics are involved, are merged. So in the block diagram you see that ALU is there, accumulator and working registers are there, program counter, stack pointer are there, clock circuit are there, interrupt circuit are there. So this is actually the basic block diagram of any kind of microprocessor, not 8085, any kind of microprocessor, basic block diagram. While in microcontroller you see that ALU also is there, register accumulator also is there, internal RAM, okay, sorry, is stack pointer, program counter is also there, clock circuit also there. Okay, input output interrupt circuit is also there. Okay, so whatever the units available in the microprocessor, those units are there in the microcontroller. Plus, it also has internal RAM and ROM. That is a very important thing because RAM and ROM section are external for the microprocessor. Okay, but in case of microcontroller it is the internal part, microprocessor it is the internal part, as well as you see the timer and input output ports. So what is we are dealing before this, before one or two class we are dealing with interrupt. So you are dealing with interrupt, and we see that interrupt is something that is coming from external device, and external device is something that is connected to 8255, that is 8255 a peripheral program and a peripheral port. So what is the 8255 purpose? Just to connect or synchronize these two devices, the external device and the microprocessor. Okay, but you can see in this microcontroller, the input output ports are available in this also. That means the function of the 8255 is also present in this microcontroller. So there is no synchronization things of problem. You can directly connect these IO ports are used in such a way you can directly connect the external devices with this so that it can directly communicate with them. Okay, also you can see the interrupt handling process is also there. So that means IO, interrupt handling process, RAM, ROM, all are interconnected in such a way so that this chip can perform a specific task very efficient manner. A specific task is performed, it can perform a specific task but very efficient manner. So this is the difference basically between the microprocessor and microcontroller. So you understand what is the basic difference according the block diagram. So the thing is that in the microprocessor we are try to make it wide application device. So we are giving only small number of units here, and whatever the other units are required for, according to the programmer or the outside world, they will bring that device and try to communicate with microprocessor. So only the microprocessor will do efficient data handling purpose. So microprocessor will do efficient data handling, arithmetic, logical unit very fast. This kind of features, basic features are available in microprocessor. But in case of microcontroller, it is a very application specific. It is a system on chip. It has a multiple number of units integrated inside that chip. Okay, so so this is the first thing you need to understand, means we are going through is the difference between these two architectures. So you can see the for second point I have already discussed. Third point is there are the instructions. So and there are many instructions in the microprocessor because it supports wide application, but here is only one or two instructions are there for moving a data from memory to CPU, moving a data between memory and CPU. Okay, So this is the difference. You can see also one or two instruction are bit handling. That means bit handling is a kind of process where data are not handled as a 1 byte combination, where each and every bit of the data is handled. So basically in 8085 there is no provision of bit handling, but in higher microprocessor there is a provision, but the provision is also very limited. So as there is limited provision, so very less number of instructions are used for that one. But in case of microcontroller, you see there are bit handling process is very has given a very important aspect of the microcontroller, bit handling process. So many bit handling instructions are there. Okay, so basically bit handling means data bit. Okay, so microprocessor can work with 8-bit data at a time, and very less number of instructions are used for bit handling, while in microcontroller you see there are multiple bit handling instructions are there, so it can easily work with each bit of a data. Also, you can see the access time, because the memory and IO devices are externally connected with the microprocessor. So time to access the data from this type of devices are more in microprocessor. But all these devices, IO or memory, are integrated part of this microcontroller. So less time is required for this. Okay. So next you can see wide sorry, you see wide application and high cost. In case of microcontroller, this the application specific and low cost. Okay. Then you see here in microprocessor, the external memory block that is connected with the microprocessor, where we can store the data and program simultaneously. So that means we are storing this data and program in a single memory space. Okay, so this kind of architecture also known as von Neumann architecture. So where we are storing data, that means that data that is used during program execution, also the program code in the same place, same memory space. But in case of microcontroller, you see there is a different kind of memory space available for data and program code. So this is very key difference between microprocessor and microcontroller with respect to memory structure. So memory, not only the memory part is integrated in the microcontroller, the memory part also have two separate space for data and program. So this is also known as Harvard architecture. So this is actually the kind of difference you can see. There's less number of pins available in for multifunction. So in a microprocessor, you cannot see the multifunctional pins, because each pin has a specific task. But in microcontroller, as the if I increase the multifunctionality of a pin, then less number of pins are required, right? So you can easily means make the efficient chip. You can easily make the efficiency. You can increase the efficiency of the chip if you make more multifunctional pins. So to increase the efficiency in the microcontroller, many pins are act as a multifunctional pins. And in microprocessor is not easy to replace, because it is a device that is connected each and every part of a huge system. So you cannot replace microprocessor, so then all total system will be damaged. Okay, but as the microcontroller is only application specific, that means if you replace a microcontroller, then only one application will be affected, no other application will be affected. Okay, so in that perspective, in that with that respect, we can see that we can conclude that we can easily replace microcontroller, but we cannot replace microprocessor. So this is this is the thing, this is the difference, very key difference between this. And then you can go through my notes. You can see what is RISC and sys. This is two kind of architecture, that is complex and reduced instruction set. So that means how the instruction set are used in a architecture, CPU architecture. According to that, CPU architectures are divided into two part, RISC and sys. So this is just a technical term you have to understand, and you have to more understand because you are from computer science background. So RISC and sys kind of architecture, CPU architecture is possible by reduced instruction set and complex instruction set are used. Okay, so there are some key differences between them. You can also easily go through it. And then I have also mentioned Harvard and von Neumann type of architecture. So what is the concept? I have already given you that same memory space for program and data, that is von Neumann, different memory space for data and program, that is Harvard. Okay, so this is actually the basic difference, and all are the very execution of the instruction take more machine cycle. Obviously execution of the instruction take less machine cycle. You have to go to the program. Suppose you have to execute some program, then you don't go to the data part, you have to go to the program part. So less number of machine cycles is required, less number of time is required for execution. So this kind of basic differences are there. Okay, you can easily go through this. Then so after this, these three differences, they are according to the architecture, memory architecture, according to the instruction, and what is the difference between 8085 and 8051. Three differences are very important, and you can easily go through them. Then I am coming to this part. This is the 8051 8051 a microcontroller, and their its key features. So this is the end of the session after discussion this part. Okay, so basically in I have jotted down only the key features, important features of the 8051. Okay, so first point is the length of the data bit that is 8051 CPU can handle, that is the length of data bit is 8 bit. Oscillator is also a integrated part. Okay, oscillator, clock oscillator also integrated part. Okay, your ROM, internal ROM, so internal ROM also, your internal ROM also a integrated part, right? Internal ROM also your integrated part. So internal, what is the ROM size? Internal ROM size, that is 4 kilobyte, right? And what is the purpose of internal ROM? This is actually your program memory. That means program code memory. That means program code memory. And you can see the RAM. So what is the size of RAM? 128 byte. So this is the size of RAM, internal RAM. And what is that purpose of internal RAM? Data memory. So you store data here. Well, you can also extend the memory size, external 64 kilobyte, 64 kilobyte. We also have some multifunctional pins, 32 multifunctional pins. We also have timer inbuilt, T0 T1 timer. We also have data communication, full duplex data communication. That means we can perform full duplex data communication here. Okay, then we have how many registers we have in 8085? Very less number of registers, but in 8051 there are 4 register banks are available. 4 register banks are available where you can have total 8 registers in each bank. That means 8 into 4 register bank. Each register bank have 8 registers, so 8 into 4 register bank, that means 32 registers are available. Okay, now program counter. So program counter locate the address of execution, next executed address. Okay, so here is also 16-bit program counter, you can see, but there is also a data pointer because the address and data are two different memory locations, so there is also a data pointer. The program counter locate the address, data pointer locate the data. So this this is also a register, 16-bit register. Okay, then you can see that PSW, program status word. So program status word is little different with respect to 8085. Okay, but the thing is the stack pointer here 8-bit length, so stack pointer is not a 16-bit. Okay, so we'll see that why it is 8-bit, right? Okay, next 8051. So what is this? So this is very simple. 8051 consists of 8-bit ALU, also it registers like accumulator, register B, PSW, stack pointer, program counter. Okay, and there is also a little difference, little division. The RAM size of this RAM means data memory, that is 128 byte. So 128 byte also used for three different purpose. Not only the data, it is used for as a working register. It is used for as a bit addressable. So I have already mentioned that it's any microcontroller has bit addressable operation. It can handle bit addressable, each bit of a data. It can operate each bit on each and every bit of a data. That means there is bit addressable memory area also available in that microcontroller. So that is the part of the data memory. So data memory where you are storing the data, and that stored data has the bit addressable memory location. Okay, and there is a general purpose memory area. So this 128 byte also divided into these three parts. Okay, so this is actually the basic features. So in this basic features you can see the size of the ROM or RAM is very important. Number of multifunctional pins is very important. Timer, their size is important. Some registers, essential registers, program counter, data pointer register, PSW, stack pointer is very important. And how your internal RAM 128 byte is divided, this is a very important features. And 8-bit length, and this is things that is very important features, key features of the 8051. Okay, so next, on the next day we will start the memory organization part. Okay, so this is not today's session, so next day we will start this. And now you give your ID. Okay, and if you have any question, then you can write it down in chat box. Yeah, there is a, I have given you some a PDF regarding memory interfacing. Okay, so if the time permits, then I will cover that topic. Okay, so let me go through one by one.